Welcome, everyone. I'm really happy today because at 8 a.m. this morning, I got this great new research result that I'm really thrilled about. And, I was so thrilled I went to sleep and had like the 3 best hours of sleep ever. So today we're going to talk about sorting algorithms. We're going to learn 8, count them 8, sorting algorithms in this class. And we're going to learn 4 of them today. Why sorting? Sorting numbers, sorting strings, sorting records in databases is really super important. You've all seen phone books. Those phone book names weren't sorted by eye. They were sorted by a computer, of course. And databases have features that allow you to extract a huge number of records from the database and sort them on any key, be it your student records sorted by last name or sorted by your parents' income. I'm sure the chancellor prefers the latter way. Google sorts your query results by relevance, and we saw last lecture that there are algorithms like Kruskal's algorithm for which sorting is a fundamental part of a bigger algorithm. And there are hundreds of algorithms like that. So sorting is one of the most essential and fundamental things you can do in computer science. So we're going to study it in some detail. Let's get started with insertion sort. So insertion sort is a very simple sort, which is probably why it runs in quadratic time, where n is the number of things or numbers or whatever that you want to sort. Now, what we're going to do is we're going to employ a list S, and we're going to maintain the invariant that S is sorted. And every time we deal with another number, we're going to make sure that we put it into that list in such a way that S is sorted. So here's the algorithm. We're going to start with an empty list S. It's easy to keep an empty list sorted. And we also start with the input. It's an unsorted list I. I stands for input of n items that we want to sort. Then, for each item in our unsorted list, we are going to take that item and we're going to insert it into the sorted list in its correct place. Now, I've written this as a high-level step, but you guys know how to do this because you've done it. You did this in homework 5, you might recall. So you know how to do that, and you know that it's a loop and it runs in linear time to insert one item. So if you're inserting n items and each of those items gets inserted in linear time, then altogether, that's n squared time. But the running time, the running time in general is n squared in the worst case, but it's for different reasons depending on how you represent your list S. So there's 2 things you could do. You could imagine representing S as a linked list, as you did in homework 5. Now, if S is a linked list, it takes theta and time, worst case time, just to find the right position in the list to insert the new item. Well, but what if S is an array? Well, we can do better than that. With an array, we can do binary search, and we can find the position to insert the new item in log n time. So that's better. But there's bad news. Once we've found the place to insert the right item, if it's in the middle of the list, we have to take all these items and shift them over one position to make room for the new item. So it still takes theta and time in the worst case. We can't win. So insertion sort takes n squared worst case time on both linked lists and arrays, but for two completely different reasons. Now, one of the nice things about insertions, well, actually, any questions before I go on? Questions? So, one of the nice things about insertion sort is that it's an in-place sort, if S is an array. And if you implement it right. What's an in-place sort? It's a sort where you can take all the items in an array and sort them and actually do all the sorting in that array using very little additional memory for your procedure. Less than linear extra memory to keep track of everything that's going on. So I will give you a demonstration of how you do insertion sort in place. The idea is this. We're going to put everything in one array. Here's some numbers I want to sort. Now, instead of having two separate lists, S and I, I'm going to store both lists, S and I, in the same array. And so initially, the array is all I, because initially S is empty. But, well, insertion sort says I take the first item in my unsorted list, and I insert it into the sorted list. How are we going to do that? Well, what I'm going to do is I'm just going to partition the array into two separate sections. There'll be, the left section will be S, and everything left over will be I. And as I go through the algorithm, I will shrink and S will grow, but everything fits in the array. So the second step is now I take the number 3 out of I, and I insert it into S in its correct place. So what happens is the 3 goes in front of the 7 moves over to make room for the 3, and the partition between S and I moves over. Then I want to take 9 and insert it into the sorted set. And 9 goes after 3 and 7, so that's easy. And the final step, I take 5 and I insert it into the sorted array. So I get 3, 5, 7, 9. And I didn't have to use hardly any extra memory. And now it's all sorted, and the unsorted input set is now empty. Any questions about that? So there's a couple of useful facts about insertion sort that you might like to know. I'll just go over one quickly. One of the nice things about insertion sort is that if you have a list that's already almost sorted, it can run much faster than quadratic time if you implement it right. Implementing it right means that when you're inserting an item, you start at the back of the sorted list and you walk forward until you hit a number that's less than 5, and as soon as you do that, you stop and you insert the 5. Now, because you're walking backward from the end of the sorted list, if you start with a list that's already sorted, it's going to take linear time to just verify that it's already sorted. The insertion steps don't take linear time anymore. Each insertion step takes constant time because the numbers are already sorted. And if you have an array that's almost sorted, then the running time is proportional to the number of what are called inversions. An inversion is when you have a pair of numbers where the smaller number comes after the bigger number. So 7 and 3 is an inversion. 7 and 5 is another inversion. 9 and 5 is another inversion. So is that all the inversions? So we've got 3 inversions in that array. So the running time is actually proportional to the number of inversions. So if you start off with an almost sorted array where the number of inversions is linear, then you have a linear time sort. But usually you're not that lucky, so we're going to go on and look for faster sorting algorithms. Another thing about insertion sort is, well, I've talked about the case where you're inserting into a linked list or you're inserting into an array. And each of them has different problems that make insertion sort slow. But I told you at the beginning of the semester that part of what data structures are all about is finding the right compromise between a linked list and an array. And one compromise we've learned is a balanced search tree. If S is a balanced search tree, well, we can find an item in log n time, and we can insert an item in log n time. So we can go process all n items in n log n time. And so that's our first algorithm that's guaranteed to run in n log n time. But I want to warn you, this is not what computer scientists are normally talking about when they refer to insertion sort. When they talk about insertion sort, they're talking about the n-squared version. So also, nobody uses this sort in practice with balanced search trees because there are just things that run faster in terms of the constant that's hidden in the n log n. So we're going to pass by this sort in favor of better ones. Before we do, any questions? Yeah. I'm referring specifically to data structures like 2, 3, 4 trees or splay trees that guarantee that the tree always stays balanced. So that's important. Yeah. All right. Our second sort is called selection sort. Selection sort also runs in quadratic time. In fact, there's a sense in which it's even worse than insertion sort because it always runs in n-squared time no matter what your input is or whether it's sorted already or not. But it's going to lead to better things, so it's worth studying. And it's also very simple. Selection sort, just like insertion sort, maintains the invariant that we have a sorted list S, and we start with an unsorted list I. So this first line is the same. The rest of it changes. So we start with an unsorted list I of n items and an empty list S, and then we just loop n times, and each time we let x be the item in I with the smallest key. And so that means we search through I, and that takes linear time, and check every item against every other item and figure out which item has the smallest key. And there's no way to get around the fact that this always takes linear time, even in the best case. So once we've found it, we remove it from I and we append it to S. And that's that algorithm. Now, whether S is represented whatever way, array or a linked list, once again, searching for the minimum item always takes linear time. So this selection sort takes theta n squared time, even in the best case. The good news is it can also be done in place. So let's come back to our favorite example here. And let's sort it again, this time with selection sort. So now, what I do is I walk through I test every item to see which one is the minimum item. The minimum item is 3. So now I swap 3 with whatever is in the first position. So 3 and 7 get swapped. 9 and 5 are still in the same place. And now I can draw this partition between the part that I've sorted and the part that still remains to be sorted. Once again, I walk through I and I look for the smallest element, and that element is 5. So I swap the 5 with whatever's at the beginning of I. So the 5 and the 7 get swapped, and the new partition is here. And once again, I look through I. The smallest number is 7, so I swap the 7 with whatever's at the beginning of I. And actually, the last step isn't going to change anything, because there's nothing for 9 to swap with but itself. So we can stop here. It's sorted. Any questions about that? Yeah? Well, if... Well, if you'd been lucky and they happened to be in that order, sure. But the reason is, if I, suppose in this case, I take 5 and instead of swapping it with the 7, I keep everything else in I in order. To do that, I would have to shift everything over one item to make room for 5 to go here. And that would take linear time, and so that blows out my time complexity. Other questions? Yeah. Mm-hmm. Well, so that's true. Every time you look for an item, it takes less time than the last time. What the amount of time it takes is going to be proportional to the sum from, well, let's say, yeah, that was right. It's the sum from 0 to n minus 1 of I. Well, actually, n minus I. But this comes out to be the same as this. Another way to look at it is the first time you do it, it takes n time. The second item you select takes n minus 1 time. The third item you select takes n minus 2 time. The fourth one takes n minus 3 time, and so on. But in the end, what have you got? You've got something that has about n squared over 2 entries. So it's true that every time you do this, it's going to get faster. But overall, that only saves you a factor of 2. It doesn't make the n squared go away. Other questions? Okay. Now, what happens if you replace I with a heap? Well, if you have a heap, you can do selection a lot faster than linear time. And that gives us another algorithm called heap sort. So heap sort is a selection sort in which I is a heap. So here's the details. Once again, we start with an empty list S and an unsorted list I. Of n items. And first thing we're going to do is we want to make a heap. The fast way to do that is this. We toss all the items onto a heap, initially ignoring the order. And then we force that set of items to obey the heap order property by using the routine that I call bottom-up heap. That I discussed at the end of the lecture on binary heaps. And you'll recall that this takes linear time to take an unsorted list of items and structure them so that they obey the heap order property. Then once I've done that, I just loop as in selection sort. And now I do my select with the removement operation. And as usual, append x to the end of S. And that's that. Now, the removement operation, you recall, takes log n time. And so heap sort is a big O of n log n sorting algorithm. Any questions about that? So heap sort, although it may not look like it at first, can be done in place. There are a number of ways to do it in place. I'll just teach one, which is what we're going to do is we're going to maintain the heap in the array. So you recall I taught you guys how to store a heap in an array. What we're going to do in this case is we're going to maintain the heap backward. So you take the order you would normally store it in the array, level order, and you turn it around, you reverse it. And so we store it backward at the end of the array. And the idea here is that as we add items to the sorted list at the beginning of the array, the heap is going to shrink towards the end of the array, with the root being in the very last position of the array. So we're going to go and sort this array again, this time using heap sort. This time we want to see what this heap looks like. So you'll recall the way heap works is that first you store the root, then you store all the level 1 nodes, then you store the level 2 nodes, and so on. But here I'm storing them in backward order. So that means the very last item is the root, and then there's the left child of the root, and then moving another step back is the right child of the root, and then moving another step back is the first item in level 2 of the tree. And so that's what our complete binary tree initially looks like. Obviously, it's not a heap, so the first thing we do is we run bottom-up heap. And bottom-up heap, well, goes through the interior nodes in reverse order, of reverse level order, and pushes them down the heap. So first the 9 goes down the heap, swaps with the 7, then the 5 goes down the heap, swaps with the 3. And so we wind up with this. Now, it's still all unsorted, but it's in heap order at least. And now we're going to start doing the remove min operation, one at a time. So I do the first remove min. And that removes the root, which is a 3. And then we move the 9 up, replacing the 3. And then we bubble the 9 down through the heap. And since its smallest child is the 5, the 9 gets swapped with the 5. And so that's what it looks like. And what it looks like in the array is 5, 7, 9, level order backwards. And now, since we removed an item from the heap, there's a space left over at the beginning of the array with nothing in it, so we can store the item that we just removed there. And then we do it again. So another remove min. We remove the 5. We move the 9 up to fill the hole. The 9 bubbles down and swaps with the 7. And in the array, the heap looks like this. From the end of the array, the root, and then its left child. And that leaves 2 spaces now for sorted items. So we put the 5 into the second slot after the 3. And then we remove the 7 from the heap. Now the heap just has one item, the 9 at the root. And because we removed an item from the heap, we have a hole that we can put the minimum item into. And finally, we can skip the last step because there's only one item left, and it's already the last item. Any questions about that? Yeah. Well, because every remove min operation takes log n time, because we have to take whatever the minimum, whatever the last item is, and bubble it down the heap. That takes log n time. And then we have to do that once for each item that we're sorting. Other questions? Okay. So heap sort is excellent for sorting arrays. For all the reasons I just showed you, but it's very clumsy for sorting linked lists. the best way that I can think of to use heap sort to sort the nodes in a linked list is to create an array. Create an array of references. Each reference points to one linked list node. Then you sort the array in just the manner that I've shown, using the references to the linked lists nodes to find the keys that you're sorting. And once you've sorted the references in the array, then you use those references to put the list nodes back together into a new sorted linked list. So for linked lists in practice, this isn't what you want to use, but for arrays, it's great. And our fourth sorting algorithm is called merge sort. Which is going to be another n log n algorithm. Merge sort is kind of like the opposite of heap sort. It's very good for linked lists. It's a little more clumsy for arrays. So merge sort is based on the observation that you can merge two sorted lists into one sorted list in linear time. We're going to do that by using two queues and sorting the items into a third queue. So let's say Q1 and Q2 are the two sorted queues which contain the list of sorted numbers that we want to merge. And let's create an empty QQ to merge them into. Then the algorithm's like this. While the input queues are not empty, we're going to check what item is at the front of each of these queues. Then we're going to figure out which one's smaller, and we're going to move it into the new queue. And eventually, after we do this enough, one of the queues will empty out. And then we just take whatever's left of the other queue and concatenate it to the end of the new queue. Now, hopefully this looks very familiar to you, because this is virtually the same as the set union operation that you guys implemented for homework 5. There's one difference between this and that, which is here you do not remove duplicates. Any questions about that? All right, well, let's use it to sort. merge sort itself is a recursive divide and conquer algorithm. What divide and conquer means is we take a big data set that we want to sort, we chop it up into two separate pieces, we sort each one recursively, and then we merge them back together into two sorted lists using our merging technique. So here's the algorithm. We start with an unsorted list, call it I of n items. We break that into two lists just by breaking it in the middle. And I'm going to call those lists I1 and I2. And one of them will have half the items rounded up. The other one will have half the items rounded down. In case n is odd. Then we sort I1 recursively. And after it's sorted, we're going to call the new sorted set S1. And then we sort I2 recursively, yielding another sorted set S2. And finally, we merge them into one big sorted list. Call it S. So let's take a look at merge sort in action. So suppose I start with a list of 8 items. So forgetting for the moment what those items are, first thing merge sort does is just chop them up into two lists of size 4. And those are chopped up into two lists of size 2 each. And in the extreme, those are chopped up into lists of size 1. So now let's fill in the numbers and sort them. So suppose my numbers are 7, 3, 9, 5, 4, 8, 0, 1. As we go down the recursion tree, they stay in the same order. But as we go back up the recursion tree, they're going to be merged in different orders. So one thing I want to say right now is that what I've just drawn here, this is a tree, but there is no tree data structure in this algorithm. This is just the structure of a sequence of recursive calls, just like your alpha-beta pruning game trees. And so one call here calls this one, calls this one, calls this one, backtracks, calls this one, backtracks, calls this one, calls this one, etc. And whenever one of these is done calling its recursives, then it merges these two lists. So it merges the 3 and the 7, it merges the 5 and the 9, it merges the 4 and the 8, merges the 0 and the 1. Now they're in sorted order. Then it goes through again, merges these two lists. 3 comes first, 7 versus 5, well, 5. 7 versus 9, 7, what's left over. Same thing over here. 4 versus 0, 0. 4 versus 1, 1. What's left over? And you merge all the way back to the top. And there are two important observations about this algorithm. Number one, the number of levels is at most 1 plus the ceiling of the base 2 logarithm of n. And 2, at each level of the tree, the amount of work that gets done, well, merging 2 lists is linear in the size of the lists. At any one level, the sizes of all the lists together is n. So we do order n work, or order n running time per level. And therefore, merge sort runs in big O of n log n time overall. Any questions on that? Yeah. Anyone else? Yeah. Well, you don't have to know anything in ahead of time. I mean, this is always going to be the height of the recursion tree when you do this. If you know what n is, then you know what you can calculate what the height's going to be. It's always the same for any given n. So one last word. Merge sort is a natural for sorting linked lists, but it is not an in-place sort for arrays. There's just no simple way, no way that's not incredibly complex to do merge sort in a single array without using basically a whole other array to do the merging in. So if you want to do merge sort in arrays, you can do it. It's just you need to have twice as much memory as what it takes to just hold your items, because you have to have an extra array to merge into when you do a merge operation. So for arrays, there are other sorts that you might prefer. And so on next lecture, I will describe the big daddy of sorts, quicksort.